Okay, so at this point we should have, we should be getting very close to finishing our projects. And if you have any questions, you should contact me or talk about them here in class today about that. Just to go over what that means, that we have a worksheet, the whole packet that was emailed to you that should be completely, all the questions answered, all the activities completed, all the drawings, the preliminary drawings done, all the preliminary evaluations for the preliminary designs done, the final drawing done, the final evaluation for the final design done, and then there should be also a bridge being built and tested. And as you're building the bridge and testing the bridge, you should be taking pictures and making a little photo journal of what you've done, and little captions with each picture, maybe little arrows pointing to things of importance that you want to point out. And at the very end, when you're done building and you're ready to test, you should take a video of each test so that you can show me a video of your most successful test. If you have any things that you have to change to your design because it doesn't pass the tests that you do, then you should submit a new drawing including those changes. And that is essentially what needs to be done for that project and all turned in to me. Doesn't necessarily need to be all turned in at once. If you've turned in, the 3 drawings at some point, which you should have done, then you don't need to turn them in again, and so on and so forth. But all those things should eventually be turned in to me. Do you have any questions about that at all? Okay, so probably the best way to do that is to lay it all down on a table and line it all up so it looks nice. Take a picture of it and text it to me or send it to me by email that way. So, yeah, that works pretty well as long as you have pretty good lighting and you get in as close as you can with the camera so that it fills the frame of the picture and gives me a nice high resolution picture. No, that's all included in the packet, the bridge building packet. So all of that stuff, everything that needs to be done is in there except for the photo journal. So the photo journal is the only thing external to that packet. Everything else, do the stuff that's in that packet. And it includes evaluations for the final drawing. It actually includes a pre-testing evaluation and a post-testing evaluation. So you evaluate your final design before you test it, and then you evaluate it after you've made the test, and then you send that to me. And that's fine if you want to, if you turn that in with your name on it and explain what that is, and that's fine. So I have to ask you, why are you so well dressed all the time? Much better dressed than the average high school student. All right. But you'd like my son. My oldest son is a junior, and he loves to dress very, very nicely. And just the other day, he wore a dress kilt, and with his vest and his dress shirt, and the proper tie for wearing with a kilt, and complete with Scottish clogs. He was looking pretty sharp. So. The only downside was that he couldn't ride his bike because he was wearing a kilt. But yeah, he got a lot of comments on that day. And I just recently I found a tuxedo jacket with tails and bought it for him as a gift so that he could wear tails one day. Anyway, you do look very sharp. Very nice. So today, let's get on and look at our schedule and make sure that we're kind of doing the right thing here. I believe that we're going to start a new chapter today. Let's see. Yes, my son discovered that we were related to the Stuart clan of the Scottish clans. We actually already knew that, but he discovered a new connection through the Stuart clan, and so he's really excited to wear the Stuart family tartans, some of which I have, but I don't have all of them, so now we have to start collecting some more tartans and have them available. There's a lot of places you can buy kilts, but there's only a couple places you can buy really good traditional ones. Of course, you can buy them from Scotland. When my parents lived up in northern England near Scotland, and they were tempted to buy me one then, but they were so expensive. And because when you buy things from Europe, they're just expensive. Europe is an expensive place to make things. But there's actually a kilt maker now in... There's two of them in the United States that I'm aware of that are making decent kilts for decent prices, and they both even make wool kilts, which is the traditional fabric. And one of them is called Stillwater Kilts. They have a website, and the other one is called Utah Kilts, UT Kilts, because they're based in Utah, and they both make really high quality wool kilts. So yeah, there are a lot of, you can buy them on eBay if you don't mind getting them from China and not being made of wool. But if you buy them from Scotland, you're bound to pay at least $1,000, and I just couldn't afford that personally. So they're very heavy too. When they're made of wool, they usually weigh about 10 pounds because they're made of like 8 yards of wool. Because of all the pleating that you have to do, you have to fold them just right so that the pattern of the tartan isn't interrupted in the pleats. So the pleats can sometimes be 6 or 8 inches deep, and that contributes a lot of weight to the kilt. Pretty crazy. All right, so what are we doing here? We're looking for the engineering course. I'm easily distracted when I'm working on the computer. Syllabus. Let's look at our schedule really quick. I believe we're pretty close to on schedule, if not actually on schedule. Today is the 21st. Yep, the 21st is a Wednesday. We're scheduled to start chapter 5 today. And we have essentially a full week to go through chapter 5, and then we'll have an exam on chapter 5 next week, and then we'll have our next project starting up next Friday. And actually, we'll start our next project actually next Wednesday, since nobody's actually in class to take the exam will just be sent to you, and you'll take it and send it back, just like the first exam. But let's go ahead and take a look at chapter 5. Before we get into chapter 5, I want to go through chapter 4. There's a couple things in chapter 4 that I want to look at just really quickly. And then we'll jump into chapter 5. Chapter 4 is about problem solving. Chapter 5 is the engineering design process in a little bit more detail, the engineering design method. So let's do this really quick. I have a really quick question for you before we get started here. As you're working on this class and working on projects in this class, are you pretty much doing this independently, or is there somebody at your school that is working as a mentor with you at all? Okay. Okay, I'm just wondering, I'm thinking of changing the way that this class is done and working with high school instructors at each high school and having them essentially be an on-site teacher that teaches things to the students in class every day and helps them with projects every day. And I mean, as a student, would you find that a better arrangement to be, you would, meet with me over the distance learning maybe once or twice a week, and then work on projects and work on different things with a teacher at your school? Would you find that helpful? Okay. Yeah, I'm working on, I have to work on this end with my administrators to see what they think of it, and then I would have to, of course, meet with teachers from the high schools to see what they think and see what the high schools think about it. But I've had so many different students from different high schools in this class that I really think it would help them, so I'm pursuing that idea. All right, so let's talk about creative problem solving. Let's turn on the document camera so you can see what some of the images that we're going to look at in here. Engineers are often considered problem solvers, and in many cases, in many ways, they are the ultimate problem solvers on the planet. They've been doing this for thousands of years, even if they haven't called themselves engineers. It is what they're doing. But problem solving is not just, a pedestrian thing that anyone can do. Very few people are tasked with actually solving problems, and even fewer people are good at it. And then there's even fewer people that are able to do it creatively and effectively and efficiently. And so that brings you down from this big group of people, or this bigger group of people that have problems to solve, to a smaller group of people to a very much smaller group of people that actually are capable of solving the problems and do it reasonably well. And then down to this extremely small group of people, which we usually call engineers, who solve the problems in a way that is really, really well done. And that's what we're trying to get to. We would like to get to become the kind of people that look at a problem and say, there is a really unique way to solve this. There is a really effective way to solve this. There's a way to do this that nobody's thought of before, or that people have thought of before, but they just haven't got it right. And we're going to get it right. And that is the key, or that is the key to thinking in the right way anyway, for creative problem solving. So here's a classic example, and there are actually hundreds of these things. In this particular puzzle, we've got 1, 2, 3, 4. We've got 1, 2, 3 dots on one side, 3 dots on another side, and of course then a matrix of these dots. So a total of 9 dots, all on this little matrix. And the puzzle is to draw 4 continuous or contiguous straight lines, right? And I think that you have to do it and go through all the dots. Is that how it works? I can't remember how this one works. There are different ones. Yeah. You want to connect all the dots with 4 continuous straight lines. So in other words, you never lift your pencil off the paper, and you are going to draw a line through every one of the dots. Okay? But you only can draw 4 of them. So you can, every time you change direction, you count that as 1. Right? Now, there are a couple of different ways to do this. Most people will, fill a page with these little matrices and just try again and again and again and again and again to solve it. Some people will sit around and just stare at it and think about it over and 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 over again. Both of those methods tend to be ineffective methods. There are other people, however, who will create some kind of a model, create some kind of a method in their mind for solving this problem. And the method will involve asking themselves questions, usually, and then answering those questions logically, using logic answers, yes or no, true or false, so on and so forth. And it is that third method, is that third idea, or that third approach, that is most often the most effective. It's the quickest and will lead you to an actual solution without trouble. Now, the point of showing you this puzzle is not to actually try to figure out the puzzle, because the puzzle is not our problem. But it does give us an idea of how to do it. If you want some practice doing these kinds of things, there are lots of these puzzles online. But we want to apply this idea of asking ourselves the questions. What do we need to do? What is it we're trying to accomplish? And what tools do we have to do it? And then starting to ask those kinds of questions and answer those kinds of questions using logic. Excuse me. Here they go through a series of problems in the section here in chapter 4 to give practice. And there's, again, nothing wrong with practicing these kind of problems, except that I just don't want to take the time to do it. What I want to look at is the problem-solving strategies here, which talks about what I was alluding to. It's 4.62 here. So in 4.62, they give us 4 steps, I think. Yeah, 4 steps or 4 things to consider as we're trying to solve problems. And first of all, you have to understand the problem, and this is often the biggest issue when you're faced with a problem to solve. For example, you might have somebody come to you and say, I need a box built to hold something on the back of my motorcycle. Okay? So you say, okay, we need a box built to hold something on the back of my motorcycle. That is our problem. Well, is it the problem? You haven't really asked them why they want this thing built to hold something on the back of their motorcycle. And so you might have to ask a question to clarify and to focus this problem. So then they say, well, I ride my motorcycle to work every day or to school every day, and I carry books to school, and I'm tired of carrying a backpack. Well, that's a much more focused problem. Okay, so now you know a little bit more about what needs to be done. Well, maybe you want to ask them what kind of books, how many books, what size of the books, how heavy are the books? Why is it uncomfortable to carry it in a backpack? Maybe because the books are too big, or maybe because they're sharp on the corners, or maybe because their back hurts from sleeping on a poor bed in the morning. They may not have a problem at all with carrying a backpack. It actually may be a problem with their mattress. And believe it or not, engineers design mattresses because of this. They take problems like this, and instead of building a box, they'll build a mattress instead. Because the mattress is actually the problem, not the books, not the motorcycle, not the box. And so asking questions is absolutely essential to figuring out what the problem is. And it's something that you should practice doing in your everyday life. When somebody comes to you and has a problem, don't try to solve the problem. Ask questions and figure out what the problem actually is. This is particularly important for men. And I don't mean to be sexist in any way, shape, or form, but men often have this I'm going to solve it persona. Okay? Women, not so much. Women are kinds of people, in many cases, not all, but every case, but in many cases, women are often the kind of people who like to ask questions and get to the bottom of an issue. They want to know more about people, and so they automatically ask those kinds of questions. Men, not so much, and it is a sex-based thing. It has to do with the kinds of chemicals and hormones in our brains and in our bodies, and it often is this way. Not always, but often. So it's important to be aware of it and to say to yourself, don't try to solve the problem right away. try to ask a question or 2 or 3 or 20 and figure out what the problem really is. You want to be careful when you're doing this with people and their real personal problems, because you don't want to be insensitive and you don't want to dig too deeply and you don't want them to think that you don't care by asking questions that are probing, because it's easy to do that. But when you're an engineer, you don't have to worry about that so much. You can sit them down at a table and you can grill them for 30 minutes because they know that you're working for their project, you're trying to get it done properly, and the questions are important. So, start asking questions. You have to understand the problem. It is very important while you're asking questions to take notes, to record the conversation in some way. I think that with modern electronics, it's a great idea just to stick your phone out on the table and press record on a little recording app that you have. And maybe even record video on the conversation. One of my favorite programs to use is a program called EduCreations, which is an online whiteboard. So you bring it up on a computer screen, you go onto their website, and it'll bring up a white page, and you can use your mouse to draw pictures on it. Or if you bring it up on your iPad, you can use your finger to draw pictures with it. But you can also bring it up on a smart board and draw pictures on it. But the great thing about it is you can press record on it, and it'll record everything that you've done on the whiteboard, but it will also record your voice, anybody who's speaking in the room at the time. There are other similar programs that will allow multiple people to log on to a single whiteboard online, and so they can all draw on it, and it will record all of their voices. And those are really cool too. What's the beauty of these things? The beauty is that you can have a discussion, you can make drawings and sketches and lists of things, and you can even pull things in from the internet, images and other things from the internet, and paste them into the whiteboard, and photographs and whatever else you can put into this whiteboard. But at the end of the day, you can press stop on your recording, and you can save that recording, and everyone can access it later. It's a very, very useful feature, and one that is used in many, many ways in engineering. So this idea of recording what you're doing when you're talking to people to clarify the question, extremely important. And I love the use of modern technology to do that. Second, so first thing is figure out what the problem is actually. Don't just take it for granted you know the problem. Don't just take it for granted that the person who has the problem knows what the problem is. They may think they know, but they may not have thought it through all the way. So figure it out. Second, find the connections between the data and the unknown. And it may be unknowns also. So there's going to be some information. You know, the person told you that they want a box, and they've told you what size they want. They've even told you why they want it. And now you're ready to build the box, but there are things that you don't know yet. And so you have to take the things that you do know, the information, the data, and you have to connect it to the things you don't know or the things you're trying to figure out. For example, you know the size of the box, you know the weight of the books, but you don't know what kind of material the box needs to be made out of. And so you're going to have to make a connection, and the connection is going to be, well, weight of books is going to determine the strength of materials needed. Size of books is going to determine the size of the box. The size of the box and the weight of the books is going to also determine weight of materials or type of materials. Because you're going to need strength, you're going to need materials that are strong enough to build a certain size box, hold certain weights and other things like this. And then you're also going to have to consider other things. You know, we know that they want to put this on their motorcycle. That's a little piece of data. Well, what do you need to think about when you are riding on a motorcycle? You need to think about the wind that's going by as you're traveling forward very quickly. You need to think about bumps on the road. You need to think about rain. You need to think about theft. You need to think about lots of different things that need to be incorporated into your design. So you need to make those connections, and you're going to start sketching them out. You're going to start sketching out all the things that you know, all the data that you have, and you're going to start writing down all the things you're going to need to know, the things you're going to need to have, and you're going to start to make connections with those things. Why do you need to do that? Well, maybe the problem is unsolvable. And that is the step where you're going to decide whether it is solvable or unsolvable. You may have, 35 books this person needs to carry, and the books are going to weigh 300 pounds. That may not be the most, solvable problem in the world. Maybe this person is a book buyer for a textbook company. They're going to have a car instead of a motorcycle, right? It's just not going to be practical. It's not really going to work to design a box to carry lots of books or something else. Then third, here they have third, carry out your plan. I might include planning and carrying out planning in the third step. But in the second step, you're certainly making plans. And so maybe the second step includes all of the planning, all of the designing and everything else. And then third is to carry out the plan. And then fourth, you're going to examine the solution obtained, which means you're going to test. You're going to get feedback from the general populace, the people who are buying your product, using your product, whatever else. And you're going to see if it worked, see how it worked, see how it could be improved. Maybe go back to the drawing board and improve it or change it or whatever else. But these 4 steps are important steps in the problem-solving process in general. So you start off with understanding the problem, making connections between things you know and you don't know, and those connections include maybe making designs, maybe making decisions, maybe whatever else. And then third, you're going to carry out that plan and all those designs. And then fourth, you're going to examine the solution that you created and see if it worked out. So, problem solving. One of the reasons I don't do this chapter in great detail is because there is a lot of math involved, and this class is not supposed to be math intensive. So we remove that by just not covering this very much. But we will get plenty of opportunities to put it into practice as we move forward into designing things and doing more projects. So let's move on. So the engineering design method, we are supposed to do section 5.1 today, and we are going to look at this book's particular application of the engineering design method or the engineering design process. I really like this book's version of the engineering design process. It's one of my more favorite versions of it. There are literally thousands of versions of this process out there. But this one can be summed up in about four or five kind of basic steps, or 4 or 5 basic sections. And I would say probably 4. But anyway, it starts off with the synthesis here at the beginning, and this covers 4 different parts of this process up here. Then it goes to synthesis and analysis, which kind of implies that it's part of this first 4. These second 2 steps are kind of part of this first 4, but also their own little thing. And so I would probably lump those 2 together. And then they have a communication section, then they have an implementation section, then they have an analysis section. So you could say 4 or 5 steps either way. But the important thing here are these different boxes down inside here. So let's look at it. Identify the need in defining the problem. Now we've just talked about that in problem solving. And it's not much different in the engineering process. You do need to figure out what the real problem is and define it. Okay, we need to define what the problem is. We need to write down a statement. Usually that statement is 1 or 2 sentences long, very concise, very clear, and very straightforward, so that anyone could understand it. Then assemble a design team. So in this class, you won't be working in teams, but if you were an engineer, you would very likely be working in a team. It is not uncommon for engineering teams of anywhere from 2 to 200 to exist. It happens all the time. So assembling a design team, and that can be a huge issue First of all, you got to figure out who you're going to need, what kind of expertise, what kind of skills, what kind of personalities. Then you got to go out there and find those kinds of people. And then you have to determine whether or not they can be on your project, because sometimes there will be a conflict of interest. Sometimes they'll be busy doing something else. Sometimes they won't be practicing engineering anymore. They don't want to do it anymore. They're retired, or they're off doing business something, making millions of dollars. Lots of things can happen as you're assembling a team, so that can be a big deal. And even though we're not going to do it in this class, you should understand that it's an important part of this process. Identifying constraints and criteria for success. So at some point you're going to need to write down, have a list of things that need to be done, have a list of parts that need to be made, have all kinds of, or maybe different tasks that we need to, that the product that we're creating needs to accomplish, or whatever. I mean, there's going to be a list of things that we need to accomplish, that need to be done to make this project work, or make this product work, or whatever it is. Let's pretend that it's let's pretend that it's some kind of device for stacking chairs, for storing chairs that have been stacked up. So, some of the things that need to be done for something like that, we need to stack as many chairs as possible on this thing, and it needs to be movable, and it needs to fit through doors, and it needs to fit in a closet without taking up much more space than just the chairs would. These are lists of things that we need to accomplish to make this project a success, or this thing that we're designing a success. And there may be, and for any given project, those things are very different and can be a lot of things or just a few things. And that's important to know those things before we even get started on design. If we don't know those things before we get started on design, we're in trouble, because our designs will not meet the criteria for success. So that the identifying these constraints and criteria for success, very important. The constraints are essentially all the things that they're things like, for example, it has to fit through a door. That's a constraint. Whereas criteria for success are more like the things that you want it to do, like rolling and whatever else. So there are some things that are considered constraints, some things are considered criteria, but they're both necessary. And then the search for solutions. So searching for solutions. You're going to go out to the internet, you're going to read articles, you're going to read journals, you're going to read other people's patents, you're going to look at other companies and see if they've done something like this, so that you're not reinventing the wheel, but maybe just improving it. You're going to spend a lot of time doing research as an engineer. In fact, probably about half of your time will be spent on a computer looking at things, reading things, measuring things, testing things, so that you can use stuff that's already been done out there, so that you can copy an idea, totally legal, totally allowed, as long as you do it properly. Maybe you're going to be reverse engineering something. This is done all the time. If you go onto YouTube and ask and search for gadget reverse engineering or something like this, you're going to find people that buy brand new cell phones the first day they come out, buy it for $1,000, and they're going to take the whole thing apart and do it on YouTube so that people can see it. It used to be that you had to do it yourself. Now you can just do it on YouTube and show the whole world. And it happens all the time. It's reverse engineering is a long-standing tradition. And people get ideas from that. They tweak designs. They build their own things, whatever they want to do. So reverse engineering is a big part of that, searching for solutions. And then eventually you're going to have a set of solutions, maybe 3 or 4 solutions that you think are going to work for you. And you're going to go through a feasibility study, which is this little arrow right here. Feasibility studies are the study that helps you, as you study your solution, study your designs that you've got, your ideas for solving this problem. You're going to study them to see if they're economically viable, see if you don't want it to be too expensive to build or to manufacture or to design or anything else. You don't want something that's going to cost your company money. So you think about economic problems. There might be engineering problems. Maybe your design is great, except it involves this one little thing that just doesn't exist. and you're going to have to invent that thing from scratch, and maybe that's just too much. Maybe it involves parts that are too expensive. Maybe maybe your design is going to require 60 pounds of platinum. Well, 60 pounds of platinum is going to make your thing worth hundreds of thousands of dollars, maybe even millions of dollars. Not happening. So you're not going to do it. Let's see. Then as you go through your feasibility studies, you will start to analyze potential solutions and choose the best solutions. But you're going to have these kind of cycles that you go through. You might analyze the best solution and then decide to go backwards and go to another solution because the one that you were looking at maybe wasn't the one you thought it wasn't the best one. And so you're maybe going to go through, and that's why they have these arrows that kind of loop back and forth, because you can go back and forth between any of these things down in here. So as you're analyzing each potential solution, eventually you're going to choose the best solution, and there will be a process to that. You will give each solution a score or a grade based on different criteria, based on economics, based on materials, based on time to design it, based on time to produce it, and all kinds of things. It'll be different for everything. But you'll analyze and analyze and analyze, and eventually you will have a best design come out. And it will not necessarily be the design you thought would come out. But if you're being honest with yourself and you're being creative and you're being very systematic, you will get the best solution out of this process. And then it will be time to figure out what you're going to do to actually produce this thing. The first thing you do after you've figured out your best solution is to document the solution in as much detail as possible. That means you need to have very good drawings of it, very good computer-aided designs of it. You might even build a computer model, a working computer model that is not just a drawing, not just a 3D model, but actually has working parts that are made of the proper materials and behave like that in the computer. This is a part of computer-aided design that not many people are aware of, but in AutoCAD, in SolidWorks, and in Creo, parametric Creo, I think that's what it's called, parametric design Creo. It used to be called Pro Engineer, and now it's called Creo. But anyway, in each of those three programs, which are the three top computer-aided design programs for engineering, you can actually design an airplane that is made of aluminum, and the computer knows what kind of aluminum it's made of because you've programmed it in. And when you test the plane, you can actually fly the plane through the atmosphere or through air because the computer knows how to simulate air. And it knows how to simulate wind, and it knows how to simulate the heating of the aluminum as it goes through the friction of air at 30,000 feet. And so you can actually fly the plane that you've designed made out of aluminum through air on the computer, and it will show you how that aluminum frame that you've designed is reacting to the air. If it's heating up too much in one spot, or if it's becoming weak because it's overheating, or if it's vibrating too much in one spot, or whatever else. And it can simulate these things. And that takes an incredible amount of computer power and an incredible amount of computer skill for the engineer, but it gives so much more, a much bigger incredible amount of information and understanding of your design without having to actually build it. So you pay this engineer, engineers get paid about $100 an hour or more. So you're paying an engineer $100 an hour to design this thing, but at least you're not building this thing for $10 million and then crashing it when you test it. Because that's the way they used to do airplanes. So this is an important part of this process, is this choosing the best solution and documenting it, because that includes so much more than it used to. It's not just drawings on paper anymore. And then communicating the solution to management, that is going to be a huge part of engineering as well, where you're going to say, I've got this design now, I've got this model of the design, or this what's called a parametric model, or a simulation of this design on the computer. Now you go to your boss and you say, look, here is the solution to our problem. This can do it. What do you think of the design, what do you think of how it looks, what do you think of the money involved that's going to take to do this, what do you think of the time that's going to take, and they make a decision whether or not that is going to be a solution that this company is going to pursue. Once they've made that decision, then you go ahead and you start to prototype. You construct the solution, you test the solution, and you verify and evaluate, which is testing the solution. And then you've got now, hopefully, at the end of the process, you've got a viable solution that makes sense engineering-wise, makes sense economically, makes sense in every way that you've gone through this process to figure out if it makes sense for it, and you're able to deliver that solution. Now, at the very end of this process, there's this arrow here that goes all the way back to the beginning. And that often happens in engineering, where you've got this thing done, now it's time to improve it, and you start from the beginning. But you don't always start from the beginning. Sometimes you start somewhere in the middle to improve a product, or to do whatever. So you don't necessarily have to go back to the beginning. But it is similar, in many cases, you do go back to the beginning because you're going to start with a new team. Maybe this is 2 years later and now they want an updated version of it. They want an upgraded version with new capabilities or whatever else. So you may not be redesigning everything, but you're probably going to start the process over again as if you were redesigning everything. So I would really like it if they had arrows on the side here that would go back into every section here. That you could go from the beginning, from the end, you could go back to any other step in the process. And actually from any other step in the process, I'd like to have a two-way arrow here so that you could go back to any other part of the process, kind of like these arrows in between. But hopefully that kind of gives you an idea of this process that we call the design process in engineering. It is more of a cycle, but a multi-directional cycle than it is anything else, where the cycling can happen at any point in this process, and it can go in any direction that need to accommodate this this creative process of designing and problem solving. And then the rest of this section, 5.1, they're just going to go through and talk about the different things that we've actually just discussed as we go through this process. For example, if we go into assembling a design team, they talk about all the different things that you would do, kind of things I talked about actually when putting together a team. Identifying constraints here, they talk about budget, they talk about personnel, people, talk about legal constraints, right? You have to be legal as an engineer. You have to make sure that nobody has patented the idea that you are trying to use, because if they have, you either have to pay them or get some kind of agreement with them that you can use that design or that idea, or you have to go with another idea that has not been patented. Material properties, off-the-shelf construction. That's a great one. If you can use something in your design that somebody else has already designed and it will work for you, and it's economical to do so, and it's going to work out, you should do that. Saves you having to reinvent the wheel again. Competition. That's something I didn't talk about. Maybe there are two other people designing the same thing or something similar to solve the same kind of problem. You want to know what they're doing as much as you can. You don't want to break the law and do any industrial espionage unless the industrial espionage you're doing is not breaking the law, because then you might want to do it. But you want to know as much as you can about the competition that you have and what they're doing so that you can either compete with them and do better, or you can keep up with them, or you can maybe take a different route. And then manufacturability they talk about. They also talk about aesthetics, how it looks, performance, quality, human factors, cost. Human factors is another thing that I didn't talk about, but there is this word in engineering called ergonomics. Ergonomics essentially means how humans interface with technology. So if you want good ergonomics, if you want something to be ergonomically feasible or ergonomically well designed, you want it to make sense to the human being. Okay, you want to make, when a human being sits down with your device, you want it to make sense to them. What does that involve? Well, that involves human experience. So what do humans have normal experience with? One of the things that humans have a lot of experience with is using their hands to do things, using their eyes to do things, and doing things in a specific way. You should never design an object where the instructions on it are written from right to left, and you're making this object for somebody who lives in the West. Because everybody that reads in the West reads from left to right. Right? So that makes perfect sense, but sometimes it's not always done that way on technology. Another great example of this is a machine that I've been using recently to do some research. Let me switch over to my computer really quick, and I'll show you what I mean. So recently I've been collecting grain from farmers out here in Nebraska, and I've been using a tool called a mini bat. It's a tool made in France, and this is what it looks like. The mini bat is it's essentially a handheld harvester. There we go. It's like a miniature combine. They don't have a really great picture of it here. You can see the front of it here. And what you're seeing as you look at this is you're seeing this from the front, so the person that's using it is standing behind it. And it's got two handles on it. One of the handles is almost exactly like, come on, stop. One of the handles on it is almost exactly like the handle on a cordless drill. And it has a battery at the bottom just like a cordless drill. It has a trigger on it just like a cordless drill. So it makes perfect sense to pick it up by that handle. The other handle is just a handle on the side here for your other hand to hang on to it. And it makes perfect sense because if you ever have a two-handed drill, that's where the handle is for the two-handed drill. And the other great thing about this is it's small, made of plastic, lightweight, so you can just hold it with two hands. And it makes perfect sense. It's really easy to use. I taught somebody how to use one in 5 minutes just the other day. There's another company in Kansas that makes something that does a similar job, does a similar thing, but it's called the Grain Goat. But look how different it is. The Grain Goat. I meant the Grain Goat. Look how different this thing is. I was using one of these the other day. How do I zoom out on this page? It's not letting me zoom out. Where's the picture? You can just see drawings of goats. I can't see a picture of the actual grain goat. Here it is. So here's the grain goat. You can't really tell from that picture how big it is, but from this picture you can. Look at the size of this thing. Hopefully you can notice from the size that we saw on the other one that this thing is about 2 or 3 times the size of it, and it's designed to be held with one hand. That's a weird picture. It's designed to be held with one hand. It's made of steel, and it's probably about, I would say, 5 times heavier. It's not very ergonomic. It doesn't make sense how to use this thing right away. And after you've used it for about 5-10 minutes, you're so tired and so sick of this job. It is very non-ergonomic. Okay? They didn't take into account the human factor. In fact, they include a strap with it so that you can put it over your shoulder, which is very uncomfortable and not very ergonomic. Okay? So, the difference is very real when it comes to ergonomics. If you think about, you can also think about video game controllers. Video game controllers, when I was a kid, they had the joystick, the first joystick, and then the first game paddles, and they were not very good for this, I'll be right out. Not very good for ergonomics, but the ones today just fit into the hands and the buttons just go with the fingers. They just make sense. So lots of things to consider as you're starting this design process, and they give lots of other examples as well. So we'll be done for today, and then we will talk again on Friday about design process. So we'll see you later. Have a good one.